Hi guys, I'm on page 36 of your AV review packet, and when you turn to 36 and you find your way there, you're going to see this empty table there. So what I want you to do just to get started with this pre-work is to click pause on my video and ensure that you're able to fill out everything on page 36 in the same way that I've done. Try to have better handwriting than me, because these are the big formulas that are going to anchor our conversation on functional analysis. So the first step to that is making sure you have all these notes written down and you're starting to internalize everything. And something extra that I've recorded is over here off to the side, my stairs, because those are the way that we navigate these questions. So it's helpful to go ahead and write those down too. So I'm going to give you a second, make sure you click pause, record everything, or just freeze the frame right here and copy my notes so that when I reference them, you have access to it. Okay, so now that you've got that done, we can go ahead and start a model problem. This is on the very next page. We have a graph of G prime. We're told G is continuous with that initial condition, 2, 5. We have this piecewise linear function defining G prime, our derivative, from -3 to 7. First question is to find the x-coordinates of all points of inflection of G for our window. So something that you just recorded on your prior page is that for G to have a poi, that means G prime is going to change from increasing to decreasing, or the other direction, decreasing to increasing. So looking at my picture of G prime, I can see that I have a change in direction right here at x equals 1 and down here at x equals 4. So to answer this question, x equals 1 and x equals 4 are points of inflection on G because G prime changes from increasing to decreasing or decreasing to increasing. You don't have to say anything other than that to get full credit on part A. All right, and on to part B. This one's a little bit more challenging because we're asked to find the absolute maximum of our graph of G given this function G prime and a justification. Absolute maxes and mins weren't actually recorded on that table on 36, so this is something we're having to recall from other situations. So when I find absolute maxes or absolute minimums for that matter, I want to make sure I'm considering various x values and then comparing the values of the function at those significant x's, critical points basically. And in order to know what x's to consider, you just have to remember you want to find your critical points or your candidates and compare them to your endpoints. So in this particular problem, I'm going to start my table at -3 and I'm going to end it at 7 because that's the endpoints of the window that's been provided. My critical points are when my derivative is equal to 0, my potential maxes and mins. So on my picture here, I've actually got 3 critical points, -1, +2, and 1, 3, 6, x equals 6. And actually, since I'm interested in just an absolute maximum, the only candidate that I'm going to consider, the only interior candidate, is this one here at +2, because that's where I change from positive to negative on the G prime graph. The other 2 coordinates I'm not going to consider because those would be potential absolute minimums, which are not significant for this question. So I'm going to put a +2 over here on my table and see if I can uncover the values of the original function. So just to start, this is kind of nice. The initial condition that's given in this question shows me that G of 2 is 5. So there's nothing crazy about that. I just get to go populate 5 on that row of my table. I'll go down to 7 next since that seems to make the most sense. To find G of 7, here's a review. I need my old value G of 2 plus the change in my derivative from 2 to 7. Here's a little fundamental theorem of calculus review. New equals old plus change. G of 2 is 5, and the integral from 2 to 7 of G prime of x captures the area over here under the axis and then this little baby triangle up on the top. And I'd urge you to pause the video for a second and ensure that you can find that area. I'm going to do the same and come back with the area for everybody because that's a pretty straightforward area computation. I want to give you time to process. Okay, so the value that I got for that is negative 7.5. The reason that's negative is because more area is under the axis than above. I do a little bit of mental math, and it looks like the function value at 7 is negative 1.5. We're going to do the same thing up here at g of negative 3. G of negative 3 is going to be equal to my old value, g of 2, plus the integral from old to new of g prime. Again, I want you to pause the video and see if you can agree with the answer that I get here. There is definitely some rigor here because my bounds appear to be backwards. So think critically and carefully about this one, and when you unpause, we'll see if we agree on the answer. All right, so I'm going to come up above here and fill this in. G of 2, whoops, let me use the pen. G of 2 is definitely 5, and I start accumulating area, and I get a negative 1.5 and then a positive 4, and you've got to be really careful with that. I'm going backwards, so my magnitudes are kind of opposite what I would expect, and I get 7.5 for that area, or that final value for g of negative 3. So to answer the question, what's the absolute maximum of our function? I look at all these results. I got an answer of 7.5, 5, and negative 1.5. The absolute max is equal to 7.5. Like I said, that's one of the more rigorous applications that we're going to see, so it's a good thing to slow down and ensure that you understood what was happening there. Okay, so in part C, we're asked to find the average rate of change of g on the interval negative 3 to 7. And this shouldn't be horrible because average rate of change is a concept you've been studying since Algebra 1. So I'm just going to populate here quickly my change in y's over my change in x. That's still just a slope formula, just like it was back in the day. I'm going to simplify my denominator down to a 10. And I'm going to look up on part B. I think we decided in part B that g of 7 was 1.5 and g of negative 3 was 7.5. So I believe I get negative 5/10 or negative 1/2 for the average rate of change here. And that's a 2-point question, guys, for just doing slopes. Okay, and now here in part D, I get another average rate of change question, but this time I'm asked for the average rate of change of g prime on the interval from negative 3 to 7. And then I'm asked a follow-up about the MVT. So average rate of change, again, is just a change in y over change in x, but because we're dealing with average rate of change of g prime, my change in y is going to be g prime of 7 minus g prime of negative 3 all over 7 minus negative 3. Just applying my slope formula to a different function now. And when I'm searching for a value of g prime of 7, I don't have to look very far because this is a graph of g prime right here, and I see that the output at 7 is 1. Similarly, at negative 3, the output is negative 4, division by 10, and I get 5/10 or 1/2. Now, the follow-up says, does the mean value theorem applied on this interval guarantee that for some value in between negative 3 and 7, we'll have another derivative that's equal to 1/2? In other words, is there a place in this picture where, let me try that again, where this slope is going to happen somewhere else at another location? Where will there be a place where my lines are parallel? The mean value theorem, I hope you remember, requires two things to be true. Number one, we have to have a continuous function for this guarantee to exist. And number two, we have to have a differentiable function. I don't have problems with continuity here, but there are tons of situations where differentiability is an issue. So does the MVT applied to this interval guarantee a value of c? No guarantee. That's because MVT does not apply because g prime is not differentiable on the interval negative 3 to 7. The reason we're not differentiable are all these cusps and sharp turns that exist between negative 3 and 7. Okay, guys, and because there's a whole other key lever that I need to address, I'm actually not going to do the second model problem. It highlights much of the same stuff, but it's calculator active, so a lot of the work would be done on a device. We'll get some practice with calculator stuff when I see you next. So for now, you can end this video, but we have one more, and that's the second key lever for me to highlight the second fundamental theorem of calculus. So be sure you watch that one too, so that you're ready for class tomorrow.